Okay, so last week we, oh, sorry, not last week, on Tuesday. What did we look at to perform learning instead of optimization, maximization, minimization? What did we do instead? Pardon? Bayesian, yeah. So what did Bayesian involve instead of doing optimization? We did what? Probabilities, but what was the operation? I was very clear about it. I remember specifically saying, look, we're not doing optimization anymore to get rid of the parameters, to find the parameters. What are we doing? Not maximization, that would be a type of optimization. But what do we do with the parameters? Set a prior, and once we'd set the prior distribution, what do we do next? Gee, were any of you here on Tuesday? You guys are really going to have to read through notes and look at stuff. Pardon? Integrate, thank you. It's really, really important you keep up. You're going to have a lot more material coming from a different perspective in the second half. If you can't answer those sort of questions, when I spend a lot of time emphasizing the ideas there, you're going to struggle. I'm actually going through this a lot slower than last year, and you really need to make sure you understand the concepts, look through the notes. I spend time providing you with reading to digest. You have to do that, okay? Because that's a really important step. You're going from a maximization of a likelihood or minimization of an error to integrating out the parameters. It's a completely different way, seemingly, of handling the parameters. Okay? So, what I want to do today is briefly look at the one-dimensional system again. Have a look at that derivation, which we didn't really go through last time. So, as I said, Bayesian inference requires a prior on the parameters. That's so you can integrate them out. The problem is, normally, in the likelihood, they're not in the right position to be integrated out. There's no guarantee you can integrate them. I brought some chalk today, actually. Normally the likelihood is probability of data given parameters. Yeah, I'm missing a few terms there. So it doesn't necessarily integrate over data. See, for a Gaussian it happens to, but that's really exceptional. So if you integrate this thing with respect to W across all W, that's not necessarily bounded. The answer could be infinity. Yeah? What we're doing in Bayesian inference to compute the marginal likelihood is we introduce the prior we integrate over this system. Yeah? So what's the result of integrating over that? What's this term here equal to? It's basic probability. First lecture, A-levels. You've got to get familiar with this stuff. It's in the tutorial. If you can't do this stuff, you don't really stand a chance of doing more advanced derivations. You need to look at that and tell me immediately what the answer to that is. What rule of probability gives me the answer to that?
Product rule.
Product rule, yeah. And so the answer is? Joint probability. P of t, comma W. If you do not see that right away, you need to read a lot about probability, yeah? I can't emphasize that enough, because how can you go ahead and do the advanced stuff if you don't see the basic stuff? Yeah? It's the product rule of probability. So this rule here, an integral over that, is what rule of probability? There's only two rules of probability, and we've done one. Sum rule. So what's the integral over P of t comma w? dw. Pardon? P of t. Yeah. So the answer of that is P of t. It's the marginal likelihood. Okay, I left out other things that could be in here, which is things like sigma squared, which is the inputs to the data x, things like that, which we're just ignoring when I apply these operations. Yeah? But that's getting the marginal likelihood out. If we put those things back in, it would be P of t given x comma sigma squared. So it's the probability of the data given only the variance and our model choice. Yeah? Which is a linear model or a polynomial, whatever our basis was. Really important. That's what we aim for in Bayesian inference. We didn't maximize the parameters, we integrated them out. What does that look like in practice? So here's a Gaussian prior, a one-dimensional Gaussian prior over the offset. So this is the example I showed last time. The offset. This is the likelihood. So the likelihood in this case, probability of the data is given by the probability of the observation we make with a mean given by the linear function, and sigma squared is the variance. The product of these two things, renormalized, gives us the posterior. So I've done two steps here actually. The first step is just to multiply the prior. This likelihood, as I just said, is not necessarily normalized in C because C is on the right-hand side of the given side. Yeah? In order to make it normalized in C, you have to multiply it by the prior, which gives us P of t comma C given m and x and sigma squared. Yeah? So what I'm then showing you here is the posterior. Now the posterior is P of c given t, but it's a result of multiplying P of c times t first of all. So where it has mass is where both the prior in blue and the likelihood have mass in the middle here. Now it then gets renormalized because if you want the posterior, you use Bayes' rule. But Bayes' rule is just a combination of the product rule and the sum rule. Maybe I should write it on here. So just using that notation we had before, P of t, can you all see this on that side? You got this, yeah? P of t given w, P of w, that's what we just talked about, gives us the joint distribution. Also, P of w given t, which is what? Anyone? Posterior, good. P of t, which is the... I hear murmurs, but I couldn't hear the... It's normalization, but we often call it the marginal likelihood, yeah? So it's the likelihood with the parameters marginalized. The process of integrating is called marginalization. The marginal likelihood, because both the product rule works for both these. This is just the joint distribution. This equality is just the joint distribution equals the joint distribution. That's all that says. Bayes' rule is simple. I mean, it's about the simplest piece of maths you could ever imagine, because it's just algebraically, we then move this under here. That's the normalization, as was mentioned here. It's not a function of w, or in this case, our w is just the parameter c. Can you close that curtain? Just there. Yeah, just pull that across so we don't have... Thank you. So this is a normalization t. It doesn't affect the functional form in w. It doesn't depend on w. It just normalizes the density. Yeah? So P of c given t, P of w given t, because w is just c in this case, we're just looking at a univariate thing, is just a scaled version of P of c comma t. So this multiplied by this and then rescaled to be normalized is all that's happening here. Yeah? So this is your prior belief. The data says, no, it's not in this region here. That's what the data's saying. Before you saw the data, you thought that maybe the parameter was here. in effect, the data's saying that offset is too low. Yeah? Your prior was that the offset was anywhere between -1 and 1, but you've seen the data, and the data is positive. Yeah, it's around here. So the likelihood says, given the noise we've assumed, sigma squared, that there's no way that the offset could be that low. So it kills that region. And the way it kills it is multiplying these together. It's like an AND operation in some sense. Yeah? Both of these things must be fulfilled, the prior and the likelihood. And the result is the posterior, which is the probability of C given that data observation. Okay? So that's what we looked at last time. And mathematically, you need to be able to do this. So we're going to go through this quickly, because I didn't actually want to spend so long reviewing that, because I actually spent quite a long time last lecture talking about that. Both of these distributions, because they're Gaussians, they have a likelihood and a prior of both what I would say is an exponentiated quadratic. Okay, so it's a square exponentiated. Yeah, this is a quadratic exponentiated. Because of the product of these two, just by simple maths, is equal to exponentiated quadratic plus quadratic, that is an exponentiated quadratic as well. So if you multiply likelihood by prior, and they're both in this form, this is the linear regression case. I'm teaching you general methodology, and we're applying it to linear regression. So these, in other cases, or nonlinear regression as well, these might not be of this form. But for linear regression, the prior and the likelihood have this form. So when you multiply them together, if that's Gaussian, what form is the posterior going to be, which is the product of these two? That. Yeah? So it's going to be what type of density? What form of density has the form exponentiated quadratic? Which I've just talked about on the left as exponentiated quadratic. Gaussian. Yes, it's going to be Gaussian. That's really, really important. You're going to be asked to recreate these derivations. And the trick is that you've got Gaussian prior, Gaussian likelihood, Gaussian posterior. It must be the case because of the maths. It's not always going to be the case. That's not a general Bayesian inference thing. It happens to be the case for this system. Yeah? So you've got a Gaussian prior, a Gaussian likelihood, Gaussian posterior. So what you need to do, though, is you need to get this guy into a form where you recognize the Gaussian. Because when you multiply these two things together, the way you do that is you just multiply out all the terms in the quadratic. Yeah? And then you end up adding them together on this side. But what you need to do is complete the square to get it in the form of a Gaussian. And that's what we'll do next. Okay, so for the system we've just looked at, this is the prior, exponential of a quadratic. All the rest is just constant as far as we're concerned. We're interested in how it varies as a function of c. That's what I've just been plotting. That's the parameter we're interested in, yeah? So the rest is kind of junk as far as we're concerned. It's important because it's part of a probability distribution. Similarly, the likelihood, which says the target minus the linear function. C appears here inside the quadratic, yeah? So when you multiply this out, it's also going to be a quadratic. So you've got e to the quadratic. What I'm just trying to say to you is, okay, in this case, a is a much more complex thing, but a is some function, a linear function of c. B is some linear function of c. Two together is just the sum in the exponential. Yeah? So it's going to be exponential. Ignoring the constant terms, the result is going to be exponential that plus that. Yeah? Then your job is to collect all these terms and rewrite in such a way that this looks like a Gaussian in C. So for it to be a Gaussian in C, the sort of form you want is C minus mu over sigma c squared. So where this is a variance associated with Gaussian, and this is a mean associated with that Gaussian. Yeah? So you have to do algebraic manipulation to do that. And the form of that algebraic manipulation is to complete the square. Okay? So that's all it involves, really, completing the square in Bayesian inference for Gaussian systems. So you're going to have to know that well. Okay. So the next point I want to emphasize is something I mentioned last week, but I just want to go through it again. It's about that scaling. Bayesian inference involves this nasty integral that I've got in an had in an isoform there. So this is the integral over c of p of t comma c given a load of stuff we don't care about for the moment. So that gives us the marginal likelihood. So integrating things is nasty. Integrating things is harder than completing the square, typically. But this thing is what we've just been looking at. Multiply the prior versus by the likelihood. The multiplication of these two is trivial. I mean, it's mechanical. You're going to need to practice it. It's in the tutorial sheet, which is online. Exercises for doing it. Multiplying these two is trivial. Doing that integral is not. But the trick is this. This term here is not dependent on c. This term here is p of t given x. Again, just ignore that. The marginal likelihood p of t, this term is, doesn't depend on c. This needs to be normalized in c. It's a probability distribution. It must integrate to 1. So it turns out that you can just sort of ignore that integral for the moment, certainly when computing the posterior distribution. This is saying is proportional to. This is proportional to this because other than this integral here, this integral is just constant in c, right? It's dependent on t and x and c and m and sigma squared, but c is marginalized. That's why we use the term marginalized. It's disappeared. It's gone into the margins. That's why I think of it like that way. So here, what we're saying is, well, this is proportional to this because we know that the term that was here is not dependent on c. Now the trick is, once you've seen that this term here is exponential of a quadratic, the only probability distribution that has that form is a Gaussian. Yeah? Once you've got the term inside the exponential in this form, you know it's a Gaussian with that mean and that variance because sorry, let's put it up here. That must be a Gaussian distribution. Yeah? So once you know it's a Gaussian distribution, you know what the constant of proportionality should be. It has to be, so I won't write it in front because people won't see. It must be 1 over square root of 2 pi sigma squared all square rooted. Yeah? That's the trick. Do you get it? So you don't actually have to do that integral because you recognize that form. You are doing that integral because you know the result of the integral because you know the form of a Gaussian density. It's in effect like looking it up, but you don't look it up. You have it in your head because you should know the form of a Gaussian density. So you don't really have to sit down and do a bunch of maths because it's a definite integral from minus infinity to infinity and you know the result. Okay. So you're going to have to sit down and do this in your own time, but the overview of it is here. I'm going to do the multivariate case in a bit. It's just a bunch of multiplying out, right, and collecting terms. The key point is that you start with a term from the prior. So this is the sum of those two exponential arguments, yeah? So you start, that's the term from the prior. Every other term is constant. It's not dependent on c. This is the term from the likelihood. Recognize them, yeah? Exponential of that is the likelihood. Exponential of that is the prior. And then what you need to do, whenever you do these things, you're interested in c, so you need to collect the terms in c. So you collect all the terms in c. There's a quadratic term in c and a linear term in c. Yeah? And then what you do is you complete the square. So completing the square involves taking, so this is a constant in c, so you don't actually care about it for computing the posterior. It's just a constant in c. This term is quadratic in C, and this term is linear in C. Now we'll do it in the multivariate case because it's a bit more complicated, but the notation, I think, looks a bit simpler. So completing the square involves deciding what a value for mu and tau must be such that when you multiply out this bracket, you recover this here. Or certainly you recover that C squared term and that C term. Any term that is not involving C just leads to constant factors, so you can ignore them because of that constant proportionality trick. So you're just trying to collect quadratic terms in C, linear terms in C, and then you try and match them to this form that you want to recover. And in this case, if you do that, what you recover is this tau squared has this form, which is the number of data points divided by the variance of the noise, plus the 1 over the variance of the prior, all inverted. And the mean has this form. Okay? Now that is what I used to make this plot. Okay? So that's what you're seeing plotted there. There's only one data point in this case, so n is 1 here. So that's the posterior. Now we're going to do that in multivariate form, which I think is simpler in the multivariate case. But before we do it in multivariate form, I have to introduce something new. I have to introduce the multivariate Gaussian. Because in the multivariate case, so what's a multivariate Gaussian? Well, I'm going to illustrate that now. So because we've now got a vector of parameters in the multivariate form, W. C and M, we want the joint posterior density over C and M. So far I've just been working with C, but we've got a vector of parameters we want to work with, W. And remember we had to use matrices to do the solution for W in the maximum likelihood case. So to do that, we need to describe vectors through probability distributions. And this is my brief introduction to what a multivariate Gaussian is. There's reading for Bishop as well for more details. This should hopefully give the intuitions. So let's assume you've got prior over height and prior over weight. Yeah? So these two different values. We've talked about there's a relationship between height and weight, but for the moment, these are models of student heights and student weights. Now, there's a probability of height and there's a probability of weight. I can sample from the probability of height, yeah, and plot once I've got a probability of weight sample. So I'm sampling for a particular student. They're quite relatively short and about average weight. We plot that on here, yeah? And what I'm showing you is a contour of a two-dimensional Gaussian made up by multiplying probability of height by probability of weight. So what we're saying is that the joint density of height and weight is probability of height, probability of weight, i.e. they're independent. It doesn't matter what the height of someone is, we just sample their weight independently. And that's a physical way of thinking about it. First sample the height, and then ignore the height for sampling the weight. And this is what that distribution would look like. It's the product of two Gaussians in two dimensions. It looks like a sort of circular hill, a burial mound. Next sample of the height, it's near the mean, and their sample of the weight is a little bit lower. So this guy's average height and about average weight. The plot ends up near the center. Okay, we can keep doing that. And we're actually sampling from a multivariate distribution. So can anyone tell me what's potentially wrong with this model for height and weight?
How do we know they're independent?
How do we, yeah, in fact, are height and weight independent? No. Weight typically goes up with height. So independence is a wrong assumption. So the body mass index is actually a bad measure of the independence. It doesn't work for very tall people. I know that. It's because why should weight go up quadratically with height? It should be cubic with any length, but even cubic is a bit odd anyway. So but people invented the body mass index to try and identify, make height and weight independent sort of thing. So what we have is actually a joint distribution that might look like this. Now these densities are the same, they're marginal densities. Looking across the height and weight, they're marginal densities. But look what's going on here. This distribution is like rotated, it's twisted. And that twist is reflecting the fact that if we expect if someone's tall, we expect them to be heavy. So this is saying that the sample should fall along a line like this. That's a correlation. So if we sample height, then typically the person will be heavy. Because if you take a height sample here and look at where, so think of this as a hill, right? This is a contour of the density, a single contour. It's really a hill coming up. If we were to slice through the hill and say, well, given we've observed this height, where would the weight be? Well, you'd have to look down there and you'd see a little bit of a distribution there. The weight is strongly constrained to be up here, rather than the marginal weight. So like once you've observed the height, you know the weight must be a little Gaussian in this region rather than this whole Gaussian here. So marginal distributions can be very misleading. Those distributions we're showing are exactly the same as these, because when you look, if you look at the hill from the height direction or you look at the hill from the weight direction, you see the same width of hill because you can't see the projection, if you see what I mean, yeah? You just look down and you see that the hill's high here and it's high here. And that's what the marginal distributions are. But the conditional distributions are very different. In this case, if you observe height, weight doesn't change. In this case, if you observe height being high, the weight is also likely to be high. So when you take samples from this system, you get these nice correlations. These correlations turn out to be crucial in posterior distributions. So what tends to happen is that we start with a prior that says our parameters are independent. So we say, oh, my prior distribution, I don't know why. I mean, why should the offset be related to the mean in a regression? It might be, but if we don't know that it is, we might start by saying the offset is drawn from a Gaussian and the gradient is drawn from a Gaussian independently, just like the original heights and weights. What the data then does is in the posterior distribution, it induces correlations. And those correlations are vital. You'll see some nice plots of them in Bishop and Rogers and Girolami for some different cases. That the posterior, you get these strong correlations. And in that case, the correlations are associated with the form of the fit. So you can see very clearly for the single data point case we looked at, if I observe that the offset is negative, the gradient has to be positive. Sorry, not negative, but small. Let's draw the axis. So I'll draw the 0 point there, so it is negative. If I observe that the offset is negative, the gradient's positive. Yeah? If I observe that the offset is highly positive, the gradient is negative. So this is the type of density you get in the posterior. Your prior says, I haven't observed any data. The offset could be anywhere along this axis in a Gaussian distribution, and the gradient could be anything positive or negative. Make sense? But now I observe a single data point, and what that data point must imply is that since I'm expecting lines to go through it, if the offset is negative, the gradient must be positive. Or if the offset is very highly positive, the gradient must be negative. So it becomes like the height and weight situation. And these correlations are vital in getting the right samples of these straight lines. Yeah? Make sense? So correlations are really important. And actually, correlations in the Gaussian density is completely uninteresting without correlations. As soon as these correlations come in, it starts to become really, I think, very interesting. So how do we get these multivariate Gaussian densities? Well, the independent case looks like this. It's just the product of two densities. Product of two exponentiated quadratics like we saw before. So just the sum of the two quadratics in the center. So it's still a Gaussian. So we've got product of those two, and we have this special form out the front, which is just the product of the normalizers. Now, oh, I'm sorry, that's fallen off the side. It's annoying. What I'm doing in this next slide, and we're just missing a bracket on this side, 2 brackets. So you can just about see that says mu1 and mu2 and close bracket. So it's just that term appearing on here. This is a matrix notation for what you've just seen. So this matrix notation this is just a rewrite of this in a matrix form. So the matrix form is vector of weight and height minus mean of weight and height as a vector, transpose times diagonal matrix, because they're independent, inverted, because the sigmas are appearing under here, times that same centered vector. If you multiply these things out, you would just recover that. So doing matrix multiplication of W minus mu1 times sigma 1 squared plus H minus mu2 times 0. And then multiply on this side gives you that first term. And doing the same, multiplying down this vector and multiplying by the far side gives you the second term. So the multivariate Gaussian we can write like this. This is just a rewrite of that, where the vector t contains W and H, mu is a vector containing the mean, and D is a diagonal matrix containing these 2 variances along the diagonal. Now the clever bit, I think, is what that form can represent. So how many of you have done 3D graphics? There we go. So this is where graphics is useful. Not that it's not useful other times, but in machine learning, knowledge of 3D graphics becomes useful. Oh, sorry, I dropped the chalk here. This form of Gaussian is what I call, or I think it's generally called, axis aligned. So if we have an axis like this, if the mean was 0, let's take a 0 mean case. Can you see over there? Is that visible yet? If a mean is 0, then it's aligned like that along the axis, with a standard deviation 1, sigma 1, and a standard deviation 2, sigma 2, giving you the directions. How can we take, if this is a 0 mean, how can we take this thing and turn it into a Gaussian with an axis along that line? 3D graphics being the clue. Sort of operations can you do on it? If you've got one line like that and you want it to become a line like that going through the origin, what operation is that?
Rotation.
Rotation, precisely. So what you do is you rotate the space mathematically. That's what I'm doing here. R is a rotation matrix. So you rotate both the input locations and you need to rotate the mean. That R actually then can pull out of this side here and just operate on the covariance. And so then you get this covariance matrix here. So this becomes a matrix. So the effect of that is to take a diagonal here. So it's got some elements here, here, and here. When you apply the rotation, so this is a standard sort of rotation matrix on here, this causes this matrix to become full. So you, instead of getting A, 0, 0, B, you get A, B, not the same A's and B's, C, D. Yeah? So it rotates the elements around. And then these become the marginal variances. These are the covariances between points. So they tell you what the correlation is. So that is the form of the covariance matrix. This now is the form of a multivariate Gaussian. This determinant of the matrix D is just the result of the product of these sigma squareds, yeah? which actually end up being called eigenvalues, but we're not going to study that in any detail, so you can ignore that. I'm missing it to the half there, sorry. It does appear here. So this covariance, instead of the normalization now, instead of being, there's a missing a half there, over 2, so and then over 2. So I'll correct those slides online. So ignore that bit for the moment because that's incorrect. But this determinant's correct. It's the determinant of the matrix, okay, to do the normalization. I don't want to go into the details of why it's the determinant, but determinants represent volumes. Quickly, the determinant is the product of the eigenvalues for a zero matrix, which, if you think about them plotted sigma 1, sigma 2, that's giving you an area. As you go out more, you get volumes out of determinants. So that's why the determinant appears in the front. It's the volume of this hill. This describes the hill. This describes the volume of the hill, ensures the thing is normalized. So read about multivariate Gaussians in Bishop and also in Rogers and Girolami. So in multivariate regression, we had these two terms. We had a likelihood where the data had the mean subtracted in this inner product form, yeah? And now we've got a prior. Now the prior here, I've written in a multivariate form. But the covariance matrix is just the identity. And that means that if we put an alpha, well, it's the identity times alpha, 1 over alpha. It's the identity times alpha, so the inverse is 1 over alpha. And that actually means the alpha just appears out the front here, because the determinant is just the product of all the alphas. So it's a very simple covariance. In fact, it's independent across the W, like we talked about before. So this prior times this likelihood. It's the same thing we looked at before. We get the posterior by multiplying the likelihood times the prior and looking at the constant of proportionality. Now let's do this slowly. Okay, so let me pull up the... So this is the multivariate case. In some ways, you know, perhaps you might think it's more complicated, but I tend to think of it as simpler. So the likelihood P of t given W, comma x, comma sigma squared. For the moment, we're going to write that as 1 over 2 pi sigma squared to the n over 2. This is independence across data points. And then here's the sum of squared errors term, yeah? Where xi is the ith input and ti is the target, the corresponding target. Everyone happy with that form? Sorry, I've missed a sum. We did this. What we did for the maximum likelihood is we just took the logarithm of this form. We multiplied it out and we optimized with respect to W. Yeah? But now we need the prior as well. The prior is again an independent form, but we're writing it in this vector form because it's going to be easier to then combine it with the likelihood. So the combination of those things, what do we need to do to get the posterior? I already sort of said, you know, here's a complex distribution form, but when we want to get the posterior, what terms do we need? Yeah, these. Yeah, precisely. We just need that and that. So for getting the posterior, we can actually just forget about everything else. And the posterior is going to, how are these going to appear in the posterior? Anyone?
Summed.
Summed, yeah. The posterior is going to be exponential of these two things summed. And what are we going to do once we've got these two things summed? What was that?
Complete the square.
Complete the square, yeah. And which terms do we need to focus on? What things are we interested in? Are we interested in t or sigma or x or w? What are we interested in? W, yeah. We want the posterior over w. So we're going to have to add these two things together, multiply out the brackets, collect terms in w, and complete the square. So we want this in a form, basically we want this in a form w minus, I'll call it mu w, transpose cw minus 1, w minus mu w. Yeah? Because that's the exponential of a multivariate Gaussian. So we want it in this form, where we've got a mu w and a cw, and the mean of the multivariate Gaussian and the covariance of the multivariate Gaussian are given by mu w and cw. Okay. So, has everyone got the prior and everything down? Can I just... yeah. I'll rewrite. So, ignoring the... right, I'll just start rewriting the exponents down here. So the first exponent was 1 over 2 alpha w transpose w, that's from the prior, minus 1 over 2 sigma squared sum I equals 1 to n. I don't know why I used that notation, sorry. Of ti minus w transpose xi squared. The annoying thing about these blackboards is they're not very... I think if you have blackboards, you're supposed to have people come around and actually wash them, which they don't seem to do. So this term's actually all right. It's already in the form we need. We want these terms in a form where we've got the quadratic term. That was c squared, because we're in vector world now, it's w transpose w. Yeah? But this term needs a bit of work. So we're going to just do what we did before. We've already done this for maximum likelihood. Aren't I nice giving you two derivations, the core of which is actually the same? To get this term out, we need to multiply out this. So it's the multiplication out of that, I'll just do it underneath, is minus 1 over 2 sigma squared. We'll leave the sum out the front for the moment. You could look at the sum on each thing. This is going to be, first term, ti multiplied by ti is ti squared, nice and easy. Second term, minus w transpose xi times, yeah, so minus 2, thank you. Ti w transpose xi. The last term, which form do I want it in? We've done this before. When I multiply this by itself...
Is it xi, then
Ooh.
wt, then w, then xi?
Almost. Right idea, wrong way round. So wt, xi transpose w. Yeah. That being the trick. You have to remember that trick. Right, absolutely the right idea. Well remembered, but just the wrong way round. Okay. So next, we need to bring the sum inside. And let's try and collect our w's in a form such as we can see what the w's are. Yeah? So I can spot, so let's bring this term down as well, minus. So which terms do we care about and which terms are unloved? One of these terms in particular is unloved. T squared, brilliant, because it doesn't depend on w. And the constant proportionality trick means that once we've written this down, we're allowed to generate and destroy terms that are constant in W as we please. We can just add 75 on the end if we like. It would have to disappear in the end when we ensure the distribution integrated to 1 by writing it as a Gaussian form. You can just ignore it. Yeah? So that means we can ignore that term straight away. But what terms can't we ignore? Any term in W. So what are all the linear terms in W? Yeah. Annoyingly, there's n of them, so let's bring the sum in. So what I want to do, well, the term that's linear in W is minus 2 sum of ti x transpose W. Sum of them I equals 1 to n. Yeah? What about quadratic? And very naughty, there's a half out the front there. Let's bring that half in and just so put that 1 over sigma squared, sorry. Just to bring the half, I forgot the half sigma squared. Terrible, this blackboard, isn't it? Okay, that's the terms linear in W. What are the other terms that we need? Yeah, thank you, yes. It should be a plus, yes. Yeah, I flipped it, just to make it in the form A transpose W instead of the form. Yeah, sorry. Quadratic terms. I want to bring all the quadratic terms together, and this is another. If you're not used to matrix algebra, there's another slight trick to what this is going to be. If I had two quadratic terms, they were AW squared plus BW squared. What would be the quadratic coefficient? A plus B, yeah. Slightly odd here because it's not written in front of the quadratic term. It appears in the middle. Just look at them, what the two quadratic terms are, and let me write them down next to each other. 2 alpha W transpose W minus 1 over 2 sigma squared. Okay, trick number 1, I mean this actually gives away the trick in some sense. W transpose, and this is the trick we did for maximum likelihood, xi transpose W. Sorry, I've gone off the side of the board. Yeah? So there's actually n terms in here. What trick did we do to get all these xi's in here? Yeah. But in particular, the sum was outside, and we've pulled the sum past the first W. How are we going to get that term involved? What do I need to change in here? Now I need to get this guy in here. Somehow I want this to appear in the form W transpose A W, where A is going to be the matrix coefficient for this equation. Very good. Very good. There's a magical identity matrix hidden in there. That's exactly the trick. Yeah? That magical identity matrix jumps out. But be careful, because we've been casually leaving these terms in front. Alpha and sigma squared. But they're different. So they're going to need to jump inside too. So the answer is minus 1 over 2 W transpose magical identity matrix times times alpha. Alpha minus 1, sorry. Alpha minus 1 times magical identity matrix plus sigma to the minus 2 times, well, I don't need the brackets probably there. It's clear without the brackets. Times the sum of I equals 1 to n of xi transpose w. Yeah? Now, we're going to have a 5-minute break. But after the break, this will turn out to be the inverse covariance matrix. Yeah? So the quadratic term will turn out to be the inverse covariance matrix. Excitingly, well, exciting for me because I said this was going to happen earlier. Look, this is the term from the prior. If you invert this term on its own, ignore that. Let's say that term's only there. The inverse of this is just alpha I. That was the covariance of the prior at the start. Yeah? And it's independent. Where did I say the correlations come from? What induces the correlations? Remember I did the diagram of yeah, from the posterior, but what pushes the correlations into the posterior? What did I say? It's the presence of what? I've drawn it. It's the only thing I've drawn on the axis. Data. Data induces the correlations because a priori you're just saying, oh, well, the offset's somewhere around here, don't know what the gradient is. As soon as you bring in a data point, it constrains, it says these things must be correlated. xi transpose, the location of the input data is what's going to is what gives you the correlations here. That's where it comes in. So this is why we have to go to multivariate Gaussians. You start with an independent Gaussian, but the likelihood induces these correlations. This is coming from the likelihood. So we'll finish completing the square after 5 minutes break while you just digest the wonder of what we've done so far. And that'll involve having, well, we'll properly identify this as the covariance, and then we'll get the mean. Okay? Good. So just, yeah, sorry, chat amongst yourselves for a moment.